Welcome to this introductory video of an MQTT-based approach for an EE architecture as an abstraction layer for the integration of vehicle functions. The EE architecture is developed by Bruno Kempf and part of a student research project at the Pixel Flux Laboratory of the University of Applied Sciences in Karlsruhe, Germany. It is divided into three parts. First, the MQTT-EE architecture is presented, followed by two scenarios that show how this architecture can improve the efficiency and driving experience in modern and future vehicles. The last part discusses a reference deployment and how to set it up for operation. This is the proposed MQTT-based approach for an EE architecture, short MQTT-EE. It is divided into three layers. The hardware layer comprises the classic devices to interact with the hardware of the vehicle. The core elements of the MQTT-based approach are the MQTT bridges. They are the transition point to the software layer. The software layer mainly consists of a high-speed bus, like automotive Ethernet, and the high-performance, centralized processing unit. The MQTT bridges transfer all data from the hardware layer to the CPU, and the other way around. The CPU also implements a MQTT broker and a wireless access point to interface with the cloud layer. The cloud layer provides real-time data and allows to implement additional vehicle functions on the fly. For efficient operation, it is necessary to form area-specific clusters on the hardware layer in conjunction with the MQTT bridges. Let us have videos which show the benefits of the MQTT-EE architecture. Consider an intersection which is approached by two autonomous vehicles from different directions. The green vehicle has the right of way and the orange one must give way. In case an obstruction, like a wall or shrubbery, breaks the line of sight between the vehicles, they cannot recognize this situation using the sensors on the vehicle. Accordingly, only when a line of sight is established the two vehicles can respond to each other. As soon as a line is established, the orange vehicle must brake to give way to the green vehicle. In disadvantageous environments, where the line of sight is not established until both cars already arrived at the intersection, strong braking is necessary. This is inefficient and uncomfortable for the passengers. Approaching the intersection with slow speed reduces the issue of passenger comfort, but braking before and accelerating after the intersection is still inefficient. Using the MQTT-EE architecture to exchange the GPS data of all vehicles approaching an intersection can maximize the efficiency and enable a smoother driving experience in autonomous vehicles. Therefore, the vehicles publish their own GPS data to a MQTT topic like the quoted one and subscribe to the GPS data of all other vehicles approaching the intersection. The topic is generated automatically, based on the approached intersection which is identified by the vehicle's GPS data. The IDs of the vehicles are arbitrary but unique to all other vehicles at this intersection. Knowing the GPS data of the other vehicles approaching the intersection, it is possible to respond without a line of sight. If the orange vehicle knows the GPS data of the green vehicle, it can calculate the time when it arrives at the intersection. This information can be used to calculate the most efficient way to pass the intersection. Depending on the time of arrival, it may be more efficient for the orange vehicle to accelerate a little bit and pass the intersection before the green vehicle arrives. Or, it is more efficient to slightly reduce the speed and give way to the green vehicle before passing the intersection. Also, This avoids unnecessary and strong braking, which will lead to a smoother driving experience for the passengers, while maintaining the efficiency. Because the vehicle with no priority can reduce the speed at an early stage. This concept is applicable to other scenarios with no line of sight. A similar source of GPS data to find free parking lots. A parking lot transmits its GPS data over MQTT while no car is parked there. A vehicle searching for a free parking lot can receive the GPS data and calculate a route to that lot. Now, the will be shown, and the setup for operation will explain based on the reference deployment. 2i, a public MQTT broker and a US beacon interface are used for the reference deployment. With the intersection scenario in mind, the US beacon interface, together with the Raspberry Pi, simulate the green vehicle that has the right-of-way. The US beacon interface is used to put the data, generated with MATLAB, on the CAN bus. The Raspberry Pi has a CAN hat and implements the MQTT bridge for the green vehicle. The CAN frames with the GPS data are mapped into MQTT messages, which are transmitted to the public MQTT broker. The public MQTT broker makes the data globally available. So, the orange vehicle, which must give way, can subscribe to the GPS topic of the intersection. Accordingly, the intersection needs a local MQTT broker to provide the data for the intersection. As mentioned before, the vehicles need to track their own global position and direction of travel to automatically connect to the correct intersection broker. A MATLAB to frames containing the GPS data. In this demonstration, the specific values are not important, which is why the CAN frames contain some arbitrary numbers. The MQTT bridge of the green vehicle runs on the Raspberry Pi, with the terminal on the bottom left of the screen. It receives the CAN frames and maps the data into MQTT messages. The MQTT message is then published on the automatically generated topic, based on an XML configuration file. The MQTT client of the orange vehicle runs on the second Raspberry Pi, with the terminal on the upper left of the screen. It subscribes to the GPS data topic of the intersection, and receives the MQTT messages, containing the GPS data of the green vehicle. Additionally, a backend server is provided, running a Jupyter Notebook server. The server is accessible from all over the world, and only requires an internet browser to write and execute Jupyter notebooks. A simple notebook can be used to apply a new XML configuration file on the MQTT bridge. The configuration file is transferred over MQTT, and the bridge automatically applies the new configuration and returns to normal operation after the update is applied. For more information on the XML configuration file, see the PixelFlux GitHub repository. To run the Raspberry Pi, clone the SMARTKART.EE GitHub repository, and run the installation script in the subdirectory bridge with root privileges. The executable file can be found in the same directory as the installation script. But first, reboot the system. To see all available command line options, use H. To run the software as MQTT, the C option must be set to true. By default, it is set to false. In this case, the software only supports receiving MQTT messages, but no bridging is performed. Accordingly, the bottom left terminal will run the software with the C option set to true, as it represents the green vehicle, which must bridge the GPS data from CAN to MQTT. The vehicle give way. It needs to receive GPS data. In this demonstration, the software is executed without setting the C option. Instead, the S option is set to subscribe to the GPS data topic. The data from MATLAB is transmitted to the MQTT bridge over CAN. The MQTT bridge generates messages and transmits them. As we can see in the upper left terminal, which represents the orange vehicle, the data is received and can be processed accordingly. Last but not least, we execute the Jupyter Notebook to transfer a new XML configuration file to the green vehicle. As we can see in the terminal of the MQTT bridge, the configuration file is automatically applied, and the bridge resumes to normal operation after it. This concludes the presentation. Thanks for watching.